Yeah, Marco, can you hear me?
Hey, Angelos.
Yes.
Hi. Angelos, I am getting a message from the instructor from Aurelio Tobias saying that when he tries to log in using the link that he received, the system is telling him that the link is non-existent.
1 second.
Sorry?
Let's see. 1 second. So, Marco, tell me again the name.
Aurelio Tobias. Let me just quickly address the participants, Angelos.
Okay, I will send you in Microsoft Teams the link again with the password, so send to him. Okay?
Okay, thank you.
Okay.
And to everyone that is joining, thank you very much for joining us. I'm gonna beg you to have a little bit of patience because our instructor is having some issues connecting. So hopefully within the next 5 minutes, we should be resolving this. Again, thank you very much for joining the workshop. Hi, everybody. Everyone who is joining us for the workshop in epidemiological methods. Welcome and thank you for sharing. We are just solving a little technical issue we're having with our presenter, and hopefully within the next few minutes, we'll be starting the workshop. Thanks for your patience. To all the task force, to all the people that are joining us, thank you very much for coming. We are just solving a technical issue that the presenter, the instructor is having with his connection, and hopefully in a few minutes we'll be ready to start. Thanks for your patience. Hi, everybody, and welcome to our workshop. My apologies for a short delay. Dr. Aurelio Tobias, our presenter, our instructor, was having some issues with his connection, but we have resolved them. So, we are now ready to start the workshop. If you just will give Aurelio a couple of minutes so that he can actually copy his presentation. He had to change computers. His computer had an issue. So in a couple of minutes, we'll be starting with the workshop. Aurelio, ¿me escuchas? ¿Estás en mute? Aurelio, can you please unmute yourself?
Yep. Can you hear me?
Great. Yes, I can hear you now. I think we can all hear you. Your camera is also on.
Okay.
So
Give me one moment that I move the files from one laptop to another one, and I will share the screen. Okay. It's 1 minute. Finally. So I'm so sorry for all the technical issues that we are experiencing. Well, I am experiencing. I think everyone else has able to be connected. Let me find, okay, here. This one, two, I move it here. Okay, almost ready. Okay.
are you ready?
Well, PowerPoint is not ready yet, but it's here. It comes. So I need to share my screen, which is this one. And you can see it, isn't it? Yeah.
You can see it now. Yes. Perfect. Okay. So let me just introduce you.
And I need to, so
Okay.
I need to,
So while Aurelio gets ready with his presentation, I want to welcome everyone to the workshop on time series designed to estimate the short-term effects of environmental health risk factors in the Eastern Mediterranean and the Middle East. This workshop is organized in the context of the second International Conference on Climate Change in the Eastern Mediterranean and Middle East, which is organized as a joint enterprise between the government of Cyprus, the Cyprus Institute, and in collaboration in this case with the Institute of Environmental Assessment and Water Research of the Spanish government, where Aurelio is a researcher. I want to give a little bit of background on who Aurelio or today's instructor is. Aurelio Tobias is an associate professor of the Spanish Council for Scientific Research in Barcelona in Spain, and a visiting associate professor at the University of Nagasaki. He holds a degree in statistics and a PhD in epidemiology and public health. His research interests focuses on environmental epidemiology and in studying the health effects of temperature, air pollution, and climate change on health, as well as the application of time series regression on meta-analysis in public health. He has published more than 250 research papers on this topic. Aurelio Tobias is also a consultant for the World Health Organization TAG group for the health effects of desert dust and a member of the EMME CCI task force on health. He also participates actively in the MMC Collaborative Research Network, which is the most extensive international collaboration to produce epidemiological evidence on associations between environmental stressors, climate, and health. With that introduction, I want to give the floor to Aurelio. Aurelio, are we set for the presentation?
Yeah. Can you see my screen?
We can see your camera right now, not your screen.
Okay, then let me reshare. And let's set my screen.
Now we can see your screen. Yeah.
Finally. Perfect.
Good.
So thanks for your patience with my technical issues. As Marco said, I don't know why my usual laptop was not working, so I need to change. I went to my kid's bedroom that fortunately is at school now, and I pick up his laptop just to run the presentation. So let's start without more delays. Just let me acknowledge Marco for the nice introduction, and also the conference organizers just to invite me participating in this pre-conference workshop. So this is the outline for today. The workshop will be split in two sessions of approximately like 40 minutes each. In the first session, I will introduce the basics of the time series regression design and the principles of the time series regression analysis in environmental epidemiology. And in the second session, I will review how to estimate the short-term effects of the main environmental health risk factors in the Eastern Mediterranean and the Middle East region, namely temperature and air pollution. And I hope I will have some time to briefly mention how to deal with desert dust exposure. Both sessions will be illustrated with practical examples using a dataset for London, which has already been used in most of the tutorial papers on time series regression. So all the examples will be fully reproducible if you download the workshop materials that you have available in my GitHub. And since we are using the same example in most of the papers, so you will be able to see how the example works not only during my presentation. You will also have the description in the tutorial papers already published. So there are two types of health effects that can be studied in epidemiological studies. The first one are the short-term effects, are those quantifying the acute impact on health after an immediate environmental exposure. And here, the time series design is the most frequently type of a study that we are using to address, to try to quantify, to assess for the short-term effects on health. And the other one are the long-term effects that refer to chronic health effects after a cumulative exposure. And this usually requires of collecting individual data for cohort studies. And both type of designs allow estimating exposure response functions that are necessary for the health impact assessment at the short or the long term. So this workshop will focus on the characteristics and practical examples of the time series design to estimate short-term effects of the, let's say, most popular or most common environmental risk exposures. So the research question that we would like to answer when addressing for the short-term effects of a given environmental risk factor, for example, let's say temperature or any given air pollutant, is the following. Is there an association between the day-to-day variation in the environmental risk exposure, again, temperature or any given air pollution, and the daily risk for a health outcome? And this health outcome can be, for example, daily mortality or daily hospital admissions for any given cause. So to answer this research question, we first noticed that the health outcomes and the environmental exposures are usually characterized by having similar time trends. So this is the example of the daily mortality, air temperature, and ozone levels in London between 2002 and 2000, the year 2006. And here you can see how when mortality, let me get the laser, perfect. How when mortality decreases, temperature increases as well as ozone, and when mortality increases, temperature decreases as well as ozone. And this is usually the pattern that we can find in winter and summer when mortality increases or decreases. But there are special summers. For example, probably the most popular one was the year 2003, where in Europe we experienced a very large heat wave that suddenly spiked mortality in most of the European cities because temperature rises much than expected than a usual summer, and similarly for ozone. So, however, we usually don't have access to individual predictors of mortality or hospital admissions beyond basic information such as maybe age or gender. And therefore, we need a study design that relies on the between daily comparison within the same population, and it should be able also to control for these common time trends between the environmental exposure and the health outcome. And this is the time series design, where we need to collect the data long enough to identify this day-to-day variation, which is necessary to disentangle the short-term effects from the common time trends between the environmental exposure and the health outcome. And this expression of long enough, we usually refer at least 3 consecutive years of daily data. So this is an example of how the time series in London dataset, the one that we will use for the example and you have available within the course materials, looks like for the first 10 rows of data. So a time series is a sequence of measurements equally spaced over time, where the unit of analysis, it's the time, the date in this case, instead of the individual person. To assess for the short-term effects, we must collect daily data. However, for other purposes, you can collect data in other time units. For example, in epidemiological surveillance for infectious diseases, for example, people working in surveillance, they used to collect the data on weekly basis instead of daily basis. So the idea is that you always need to keep collecting the data always in the same unit. That could be from annual to monthly, weekly, and even hourly. But as I mentioned, just to assess for short-term effects of environmental exposures, we used to collect data on daily basis. The time series design has some strengths. The main ones are the use of administratively collect data, for example, from national statistics, health departments, or city councils. This data used to be available, and in most of the countries is almost for free. You only need to fill the application just to justify that this data is for research. And here in the time series design, the good thing is that the population is compared with itself. So we are following the same population over time. So individual factors or individual risk factors, like for example, gender, age, smoking, or even drinking alcohol, are not changing in their frequency over time on daily basis. So we said that we don't need to account to control for this usual time invariant or slowly varying individual risk factors, because they are not having the same time trends as the health outcome. So in a classical cohort study or in a classical case control study in epidemiology, we always need to account for these potential variables that can confound the effect of the exposure over the health outcome. But at the daily level, since the distribution is not changing over time with the same time trends and the health outcome, we don't need to account for these variables. However, we can study if there are different effects of the environmental risk factor by gender, by collecting for example, the daily mortality by males and the daily mortality by females, or by age, just by collecting the daily mortality for those below 65 and those who are older than 65 years old. But the design also has some limitations. This is a kind of ecological design based on aggregate data, since individual data is not available. So we can only make inference about the effect on the populations, not at the individual level. So we cannot either to study long-term effects. We cannot study chronic effects on health with this design. It's only available for short-term effects. And it's quite sensitive for the choices that we will see later on for the modeling of the time trend. So we need to account properly on the way that we deal for these common trends between the environmental exposure and the health outcome. So here, among the regression models that we have available in environmental epidemiology studies, we used to work with Poisson regression to analyze the data. And this is because Poisson regression is the appropriate regression model to use when the outcome is a count. So, and in our situation, in the time series design, we are collecting the daily number of a given health outcome. So we are collecting daily counts of mortality, for example, or daily counts of hospital admissions for any given cause. This type of regression model, the Poisson regression model, also is a model familiar to the epidemiologists because it allows estimating the effects as relative risk of mortality or hospital admission, as I mentioned, for 1 unit increase of the environmental exposure that then can easily be transformed as a percentage risk increase. And the relative risk and the percentage risk increase are epidemiological measures of effect, which are quite familiarized to not only to the environmental epidemiologists, to any given researchers working in health research. So, but there are a couple of model assumptions that we must to consider carefully. So the first one is related to the Poisson regression itself. And this model assumption refers that the variability should be equal to the mean. And the thing that we often find is that the counts of data that we collect have a larger variability than a mean value. And it happened that when this happens, it tends to underestimate the standard errors, and then all the inference that we are making about the effects of the environmental exposure may not be valid. But the usual solution is instead using the Poisson regression in your usual statistical software, the one that you are using to analyze your own data. You can select using the quasi-Poisson family distribution within the regression model. This is an option which is available in almost most of the statistical software that allow to analyze regression models with Poisson regression. And it only adds a kind of estimation of the over dispersion in your data, and automatically by default corrects all the standard errors. And the second limitation, or the second assumption, it's mainly related to the time series regression, because a key assumption for regression models is that the outcome measures must be independent and identically distributed. This is one of the first things that you used to learn in a regression course. But in time series, closer events tends to be more similar than those further apart in time. So after fitting, let's say, the linear association between the health outcome and a given environmental exposure, the residuals need to exhibit a kind of independence. But as you can see here in my example, the residuals, they are still showing some kind of seasonal dependence over time. So this problem of the residual residual autocorrelation can also affect the standard errors, and therefore make not valid all the inferences or all the short-term effects that we are trying to estimate using our regression model. But we will see now how can we sort out this problem or this assumption of the related to the autocorrelation in the data, that we need to be independent in our regression models as a main assumption. So in the time series design, you need to remember that because being an ecological design, working with aggregate data, is a type of observational design, and therefore with a high risk of bias. In epidemiology, we used to define a confounder variable as a variable which is associated with the exposure, also independently associated with the outcome, and it not be in the causal pathway between the exposure and the outcome. Thus, in the time series design, time itself is a confounder, because as I mentioned before, both the environmental exposure and the health outcome are showing the same time trends. So somehow we need to account for the time in our analysis. So this is a classical example from Yule that was published a long time ago in the mid-20s. So he collected the annual mortality rate, which is in the red color, in England and Wales between 1850 and the beginning of the first century. And he also collected the rate, the number of marriages in the church, or by the church of England. And when he correlated both, he saw that the number of marriages almost predict perfectly the mortality rate. So a policymaker these days could think that it could be useful to forbid people getting married as a public health action, because it could help reducing mortality. But the thing that they didn't take into account is that here, once again, both series, the mortality rate and the number of marriages are exhibiting the same time trends. So after correcting, or after accounting in a right way for time in this analysis, you can see that the correlation becomes null, meaning that the number of marriages does not make any sense for or to predict the mortality rate. So, but how can we account for time in our regression analysis? So the thing that you need to know is which is the modeling framework for a time series regression model. So this is mainly coming from this temporal decomposition. So any given time series data can be structured in at least 3 components. The first one is the long-term trend, how the time series increases or decreases in average over time. The second one is the seasonal pattern. How is the seasonality within each year? And this seasonal pattern repeats with the same, and this seasonality repeats with the same pattern over time. And
I think we're having a connection issue with Tobias. Please hold on while I try to reconnect him. Hi, everybody. We apologize. There seems to be a problem with the connection. We're trying to solve it. Can you please confirm in the chat whether you guys can hear this announcement that I'm making? Perfect. Thank you. I think everybody can hear me. Thank you very much. We are resetting the connection with Dr. Tobias, and hopefully in a couple of minutes he'll be back online. Again, many thanks for your patience.
Can you hear me?
Yes, already we can hear you now. And if you just restart your presentation.
Okay, let me reshare. Can you let me know where?
Okay, go back a couple of slides. Go back one slide. One more.
Here?
Yeah, I think right after you finish with this slide, is that the connection started to fade. There we have. Okay.
Okay, so sorry guys. It's Murphy law. So okay. We were saying, or I was trying to explain before the connection was down, that we need to filter it out to remove the time trends that the data exhibits. And for the reason, you need to know which is the modeling framework that we are working with in the time series regression. So this modeling framework implies that any given time series can be decomposed in three parts. The first one are the long-term trends, meaning how the health outcome increases, or in this example, decreases over time in average. So the second one is the seasonal pattern, how the cycle is repeat over the years, which is the one illustrated into the middle panel. And the last one is the one that we named the residual component, which is how our health outcome time series will look like after removing the long-term trend and the seasonal pattern. So how can we do this decomposition process within the regression model framework? So we can do this in a very simple way. So we can filter out the time trend using dummy variables for year and month. So here the first figure shows how the long trends adjust after fitting the year into the regression model. So the middle panel shows the seasonal pattern after adjusting for the month. So it shows or exhibits the seasonal pattern. And the last panel shows the prediction when combining both year and month into the regression model. So this approach is quite easy to understand and often captures the main long-term patterns. However, assumes a kind of implausible jumps in the health risk between close months, because we know that time is a kind of continuous, it's not going jumping, the risk is not jumping month to month, so it's changing day to day. So we can use a kind of we can use an alternative approach by using periodic functions of time. Here we define Fourier terms as pairs of sine and cosine functions of time to model the seasonal variation in the outcome as a regular wave each year. So the first plot, once again, the one at the top, shows the filtered time trend, assuming an annual seasonal pattern. It's repeated once every year or once every 12 months. The middle panel shows the fitted time trend, assuming a kind of biannual seasonal pattern, so changing twice every 6 months. And the last panel shows a quarter seasonal pattern, meaning it changes, seasonality changes every 3 months. So, however, the model seasonal pattern is forced to be the same each year, which may be not reflect the data well enough. So for this reason, in most of the environmental epidemiology studies, we prefer to use splines functions of time. So a spline is a set of polynomial curves that are joined smoothly end to end to cover the full study period. So the amount of smooth is defined by the number of degrees of freedom per year. So roughly the interpretation is for this specific parameter, the degrees of freedom per year roughly is that the times that the data can change the direction of the time trend within a year. So for example, the first plot, the one at the top, shows the fit time trend with a natural cubic spline with 1 degree of freedom, so meaning it only allows to change once per year. And as you can see, it's mostly linear, only capturing the long-term trend. So the middle panel shows the time trend with 6 degrees of freedom per year, capturing quite well a similar seasonal pattern for each year. Although here you can notice that it's not forced to be exactly the same as with the periodic functions. They are similar enough, but not exactly the same. They are adapting well to the data. And the final panel uses like 12 degrees of freedom per year, showing a bumpy fit, which is a kind of indication of over-adjustment. So once we already know the modeling strategies that we have available to fit or to adjust to capture the time trends in our regression model, so we can compare them. So, and we can compare them in terms of the model assumptions that I mentioned before, over-dispersion and autocorrelation. Here we notice how the use of the spline functions minimize the over-dispersion, which are the values that you have at the top of each figure. That it should shows a kind of phi Greek letter, but it seems that in this computer is not taking well the symbols. So this 1.20 in the last panel means that the standard errors are for a Poisson regression model are or should be inflated like 20%. But as you can see, for the periodic functions or using the most simple approach with a time stratified model, the amount of over-dispersion is much larger. And the same happened with the residual autocorrelation. The plots that you are looking here are named autocorrelation functions plots, and each of these points are the correlation between the residuals from the Poisson regression model themselves. And as you can see, the one that minimized this residual correlation that almost achieved that the residual values fulfill the key assumption of any given regression model of being independent and identically distributed are the one using splines functions of time. So finally, you may ask how to select or to choose the right model among the alternatives. So when you decide, for example, to use the splines functions approach to model for time, you need to choose, as I mentioned before, which is the smoothing degree for the time trend. If this smoothing degree is too low, then you will only be able to capture the long-term trend and you will miss the seasonal pattern. But if you use a very large number, so the thing that will happen is that the fitted values will be too bumpy, and then you will be overestimating the effect that the time trend has on the data. So here you can use, for example, you can use several methods. You can use, for example, regression diagnostics, mainly based on the inspection of the residual values from your Poisson regression model. This is always useful just to identify deviations from the model assumptions, as we have seen for the overdispersion and the residual autocorrelation. You can use statistical criteria, such as information indices, for example, the log likelihood ratio test, to compare between nested models or the Akaike information criteria, or even looking, as we did, to the autocorrelation functions, tries to look which is the one that minimize the residual autocorrelation. However, none of these methods has been proved as a general and flexible, as a general reliable method. So a priori assumptions based on the epidemiological literature and sensitivity analysis are recommended. So in other words, once you choose the number of degrees of freedom just to smooth the time trend in your analysis, it is always recommended just to try a value, a lower value and an upper value, just to check if you are underestimating or overestimating based on your choice. So, and this is the summary for this first and very accidental lecture. So the time series studies provide evidence on the short-term associations between environmental exposures and health outcomes. And the time series regression is similar in principle to any other regression analysis that you are familiar with, but with some specific features. The ones that imply characterizing in a proper way the time trends and seasonality, and then checking for the residual autocorrelation, just to check if you are fulfilling, after controlling properly for the time trends and seasonality, one of the key assumptions for any given regression model, which is that the observations must be independent and identically distributed. So do you have any questions? Or maybe we can move forward to the second lecture, and then we can answer all of them.
Aurelio, I suggest we move forward given the time delays we have had, so that we can cover everything.
Okay.
And then the questions we take online where we can, and then if people has more questions, then they can communicate with you privately later on.
Okay, perfect then. So then let me go open the second lecture. Oh, so let's go then. Let's go for the second lecture. So the second lecture mainly focus on, once we already have our core or baseline model, which is the one that you already been able to control for time trends and seasonality, is how to use this time series regression model to quantify for the short-term effects of environmental exposures. So in this session then, I will focus on how to model the association between the environmental exposures and the health outcomes. And these associations can show different types of shapes and are often characterized as well by lagged effects. So therefore we need...
Aurelio, excuse me, we cannot see your screen. I don't know if you're presenting anything. We cannot see your screen right now.
Why is not getting... Si lo ha seleccionado. It's probably the most... No.
It was fine a second ago when you changed the presentations.
I got an automatic message saying that stop application sharing. They close it. Okay, I will try it again.
Okay, there we go. Now we're gonna see it.
Can you see it now?
It's coming. It says it's starting to share content, so I think it's loading.
Now.
Not yet. Now, yeah, now we can see it.
Okay,
Yes,
perfect.
now we can see it.
So, I'm sorry, guys. So, I was telling that the associations can show different types of shapes and are characterized by lag effects as well. And we will need to model this complexity in the temporal patterns of the risk due to time-varying exposures. And to do this, it's always important to remember that we need to base most of the decision in the previous knowledge about the shape of the exposure and the lag effects. And we will see how. So for example, I will start focusing first on the exposure response of temperature, because it is well known that the relationship between temperature and any given health outcome, for example, mortality in this example, is nonlinear, showing a kind of U shape, as you can see in the figure. Thus, here, you can fit a quadratic model after adjusting for time, of course. So if you check carefully, so you could see that in my model specification, I already include a function of time that, as I mentioned in the previous session, it has been done using a spline function of time, natural cubic spline. So here we can fit, or we can start fitting a kind of quadratic model where, and from this quadratic model, we can estimate multiple effects of temperature from the model parameters. In fact, we can estimate a different effect for each degree of temperature. And also under this approach, we can even estimate from the model parameters, which is the temperature where the mortality shows the minimum risk. This is the one that we used to name as minimum mortality temperature. And an alternative approach for a more straightforward interpretation is by using a piecewise linear model. So this model only has two slopes, one for cold and another one for heat, reporting through the model parameters how the risk of mortality increases or decreases for a rise of 1 degree of temperature above or below the minimum mortality temperature. And this minimum mortality temperature can be identified empirically. However, in environmental epidemiology studies, we prefer to use, once again, a more flexible approach using splines. So here we can easily identify the minimum mortality temperature at the minimum of the exposure response curve, as you can see in the panel, and estimate the cold and the heat effects by comparing the risk at the low and high temperatures, that in this case, we set arbitrarily that the low temperature, it could be the 2.5 percentile of the temperature distribution, and the heat could be defined as a high value of the temperature distribution that, for example, here, I did use the 97.5 percentile. And then we can compare the risk at these values with the risk at the minimum mortality temperature point. And this is the way that we define the cold and the heat effects when using a spline function to estimate the exposure response of temperature. So, however, the previous examples, the previous exposure response shows the effect of today's temperature on today's mortality, or the effect of today's exposure on today's health outcome. But yesterday's temperature can also affect today's mortality. Is the one that I have defined as the heat effect of today's temperature on today's mortality. So the second one is how does it look like the heat effect of yesterday's temperature on today's mortality, of 2 days ago temperature on today's mortality, and so on up to 3 weeks. And we can do the same for heat and cold. And from the top panel, you can see that the heat effects used to be at the short terms, up to 1 week, and the cold effects, this looks like to be longer, up to almost 2 to 3 weeks, starting 1 day after the exposure. But as I was saying, today's temperature affects today's mortality, but will also affect tomorrow's mortality and will also affect the day after tomorrow's mortality, but to the lesser extent, and will also affect mortality in 3 days, even lower 4 days, and go on up to 1 week. This is, let's say, the kind of forward perspective for the lagged effects. But we can think also in the backward perspective, thinking that today's temperature affects today's mortality, but yesterday's temperature affects also today's mortality. And 2 days ago temperature affects today's mortality, even to the lesser extent, and so on for the 3 days, for the temperature of 3 days before and 4 days before, up to 1 week before. So as you can see here, this concept of delay or lagged effects can move interpretations forward and backwards, providing almost reporting almost the same idea to interpret the lagged health effects of any given environmental exposure. But in a similar but this means, this means that when looking at the independent effects, this means that we need to run an independent model to estimate the health effects for each lag. So in this example, I was trying to assess for the health effects of heat for 3 weeks. It means that I should run 21 independent Poisson regression models, adjusting for time and fitting the exposure response for temperature using a natural cubic spline. But under the previous idea of the meaning or the interpretation of the lagged effects, both in backwards and forwards, this means that today's effect is also influenced by yesterday's temperature, 2 days ago, temperature from 2 days ago, 3 days ago, and so on. So in other way, any of these given heat estimates are exhibiting a kind of cumulative effect from the previous days. So they are not the independent effects of today's temperature and the day before, the temperature from the day before, 2 days before, and so on. So the way that we can achieve these independent effects is by fitting all the lag variables for temperature into the same regression model. In other words, running a unique single time series regression model fitting the temperature from today's temperature down to the lagged up to 3 weeks. However, the thing that happens when looking the results from this model is that the effects are being reduced, and it seems that they are only appearing in the same day that the temperature happens, and even one day before. But for all the other days, the effect seems to disappear. And this is happening because all these 21 variables related to the lag temperatures that we already fit into the model are highly correlated. So today's temperature is highly correlated with yesterday's temperature, and yesterday's temperature is highly correlated with the temperature 2 days ago. So this model that we named the unconstrained lag model, it's highly affected by multicollinearity. So therefore, we need to constrain somehow the heat effects by, for example, forcing to estimate the same effects for a given set of days. So in the top right panel, yep, shows the heat effects being the same, forcing to be the same for the first 3 days, for today's exposure, yesterday's exposure, and 2 days ago exposure. And then I force a second condition, which is being the same up to the 3rd day, down to the first week, and then force being the same for the 2nd week, and down and to be the same for the 3rd week. And here we can see once again the short-term effects are quite clear for the first 3 days, and then they disappear after the 4th day. But these jumps in the heat effect, that's not seem biologically plausible. So we will expect something more continuous. And for this reason, once again, we can constrain the lag effects by using an spline function to show them in a continuous way, as you can see here in the bottom right, at the bottom right panel. So in other words, we need to account for the exposure response and the lagged effects. And this can become quite complex because the exposure response can change across the lags. To take into account this complexity, we can use, or we can define, a kind of bidimensional exposure lag response function, which is defined, or which is known as the distributed lag nonlinear models. And this is the approach that we are mainly using in environmental epidemiology to assess for the short-term effects of any given environmental exposure. So when using a distributed lag nonlinear model to estimate the short-term effects of any given environmental exposure, once again in this example is temperature, the result mainly comes from this three-way, or it turns in this three-dimensional surface, which is a combination of how does it look like the risk of mortality at different temperatures for different lags. And of course, we can derive a kind of overall effect by collapsing or reducing the lag dimension. So in other words, it will be like pushing from the front down to the end this figure, and collapsing all the lag dimension into a single one, and then we can see at the bottom how will it looks like, showing the usual U shape that shows the association between daily temperature and mortality. So, however, you can also choose to show the results in terms of the exposure response slice at different lags. how does it look like the exposure response after 2 days of the temperature happens, or after 1 week. So, and it's up to you to choose which are the slices that you would like to show in your paper, in your report, or in your work. But you can do it as well in the other way around. So you can show the lag effects, slicing and specific ranges of temperature. So you could, as I mentioned before, so you could get the slice for heat, for example, taking a high temperature of 22 degrees in London, and how does it look like the cold effect by choosing a lower temperature, for example, 2 degrees. And here we can see how heat affects mortality at short terms, just before 1 week, but cold has a more longer effects up to 3 weeks. And this is the way that we summarize the results when we're trying to estimate the effects of temperature using DLNM models. But temperature is not the only exposure. So at this stage, all my examples have been focused only on temperature. This is the way that we analyze the data, and we got the knowledge that we already know. So for temperature, we already know that there is a nonlinear association for most of the health outcomes, showing a G, V, or even U shape that can be modeled, this complexity, in a relatively easy way by using this family of models named DLNMs, distributed lag nonlinear models. There is a minimum risk of mortality or hospital admissions or any given health effect at the point that we used to name it minimum mortality temperature. And there are short-term effects for heat, up to 1 week most, but the effects for cold are much longer, up to 3 weeks. And in a similar way, we can analyze air pollution. So using similar methods, we will see now an example. So we already know that for all the pollutants, or for most of the pollutants, the association is much simpler. The association is most linear. So there is also a minimum risk, which is of mortality, which is set at the minimum air pollution exposure in each location. And the health effects of air pollution are usually short-term effects, up to 2 to 3 days maximum. And now it comes a kind of important part when trying to assess the common or the effects of the environmental exposure in a common way. So the thing that happens is that if you remember of my definition of confounding in epidemiological studies, so here we have that temperature is associated with mortality, independently of air pollution, and air pollution is associated with mortality. But temperature can also be associated with air pollution. And under this definition, here we can say, or we can conclude, that for temperature, air pollution is not a confounder. So for this reason, in most of the studies, in most of the epidemiological studies trying to assess for the short-term effects of temperature on health, these studies they don't take into account air pollution, because it's not necessary. Air pollution is not confounding the effects of temperature on the health outcome. But since we know that, because of this causal diagram, that temperature is a confounder of the association between air pollution and mortality, the effects of air pollution on health, these ones are strongly confounded or even modified by temperature. So in other words, in the studies that they are trying to assess for the short-term effects of air pollution on health, they need to control for, in an appropriate way, not only for the time trends, but also for temperature. And this is the example. This is how does it look like the overall exposure response function for temperature and ozone in London. When I mean here unadjusted, it means without taking into account the time trends. As you can see, well, for temperature, it still exhibits this U shape. But for ozone, it seems that when ozone increases, the risk of mortality decreases, meaning that ozone can be a protective factor instead of a risk factor. When we adjust temperature for time trend, in the way that I already mentioned, so using in the method that you prefer most, so the time stratified model, the periodic functions, or the usual that we are working with in environmental epidemiology studies, which is with the spline functions, we can see that for temperature, it keeps showing the U shape, but if you check carefully, now the cold effect is more pronounced, and the same for the heat effect. And also, if you look very, very close to your screen, you will notice that the point of minimum mortality temperature has been increased for a bit more than 1 degree after adjusting for time trend. But it's more surprisingly what is happening with ozone. With the air pollutant, the trend change dramatically. It moves from being a protective factor to a risk factor. Now, after adjusting properly for the time trends, the thing that happens is when air pollution increases, the risk of mortality, of course, increases. But what's happened when we are trying to assess for confounding between temperature and ozone, or temperature and any other given air pollutant? So as you can see, after adjusting for time trend and ozone, the shape for the exposure response of temperature does not change, remains exactly the same. So therefore, when we are trying to estimate the risk of heat and cold will not change after adjusting for ozone, but the slope for ozone is being reduced substantially after adjusting for temperature. So this is the confounding effect that I was mentioned before between temperature and air pollution. Temperature confounds the association between air pollution and health, but air pollution does not confound the association between temperature and health. So if your main interest is trying to assess for short-term effects of air pollution, of any given air pollutant on human health, you always need to account for the effect of temperature in your time series regression model. So, and in my previous slide, I was mentioning that estimating the effects of air pollution is much more, let's say, straightforward, because the association is always linear and it's more at the short terms, maximum 2 to 3 days. Here, this is the exposure response function for a distributed linear, a distributed lag linear model. So instead of DLNM, we name it DLM, because the association is linear instead of non-linear. And as you can see, the slope changes lag by lag. And this is the overall slope. Once again, the overall estimate, like trying to reduce to collapse the lag dimension. Here, just only for illustrative purposes, I did extend up to 1 week lag, up to 7 days, just to show more clearly how does it look like the risk surface for ozone. If we look carefully, lag by lag, we will see that for the first day, I mean, ozone's temperature does not seems to be negatively associated with the risk of mortality. but yesterday's exposure and the exposure from 2 days ago and even from 3 days ago increases mortality. And these are the short-term effects that we are looking for. So usually the short-term effects of any given air pollutant, it's at 2 or 3 days maximum, because after the 4th day, the 5th, and even if you would like to replicate my example with the R code that I already put into the GitHub, you will see that for day 6 and for day 7 looks like exactly the same as for day 4 and day 5. And here it's even estimating the effects of ozone is even much easier than for temperature, because we only need to summarize how much is the slope, how much increases the risk for a rise of, for example, 10 micrograms per cubic meter of ozone. And we can do so by estimating or just by plotting how much are the slopes for these 5 plots. So as you can see, for today's exposure, there is no risk, but the risk increases substantially 1 day after the exposure to ozone occurs, 2 days after, and start decreasing at the 3rd day, and from the 4th up to the end of the week, up to the end of 1 week of exposure, the effect almost disappear entirely. So I think that we still have give me just few minutes to talk about the desert dust exposure, because since this workshop was mainly was included in the conference on climate change for the Eastern Mediterranean and the Middle East region, this is desert dust exposure is a kind of important environmental risk factor that needs to be addressed in a proper way in this region. So desert dust exposure is a completely different story, because it mainly depends how desert dust exposure was measured, how was defined. And it could be defined using a binary metric, just by identifying which days were affected by a dust event and which days were not affected by a dust event. And this can be done in many different ways. This can be done just, for example, checking to aerosol maps, meteorological products, satellite images, or even using a threshold for air pollution due to particulate matter. So, for example, in most of the countries in the Middle East, they have a threshold of 150 daily average micrograms of PM10. So, but my point here is, once you get to define the exposure in a binary way, days affected and non-affected by a dust event, this is the research question that you would like to answer. Is the occurrence of a health outcome higher on dust days compared to non-dust day? So is the mortality increases on dust days compared with the mortality on non-dust days? So in other words, here we are trying to compare if the mortality during dust days, which are those mark or shadow highlighted in this shadow color and marked in with a black dot, is are larger than those who are hollow, meaning that they are not occurring during that they are occurring during a non-dust days. So the problem here is that under this approach, the problem is that all dust events are treated in the same way, and therefore they are not providing information of the exposure, of the shape of the exposure response. So, and it may be affect more health a day with a very large dust storm than with a day when the amount of dust was quite low. To solve this, this binary metric can be used in another way. It can be used as an effect modifier of the association between air pollution by particulate matter on health. But if But for those studies trying to address this, the use of the binary metric as an effect modifier, please be careful checking that they are trying to answer a completely different question. Here, the different question is the occurrence of a health outcome? Oh, sorry, the copy and paste. So here, the research question, I will update this back into the slides that I already placed in the website. Here, the research question should be something like, is the health effects because of particulate matter larger in days affected by dust than those non-affected by dust? Because the main exposure is not dust, the main exposure is the particulate matter. However, once again, under this approach, it is not possible to attribute the health effects of dust to a given source, because both are, let's say, mixed into the particulate matter, which is the main risk exposure that we are trying to assess the health effects. The only thing that we can assume is that, as you can see here, those days affected by dust, they tend to have a larger concentrations of PM10 or coarse particles. However, this large amount is affected by dust, but it also, there is a part which is produced by the local emissions, mainly by traffic exhaust. So it will be ideal if somehow we can quantify the dust by itself. So if we can disentangle the sources of PM, if somehow we can quantify how much amount of the net of PM is because of the natural source, on how much of the amount of PM concentrations is because of a local source. If we are able to do this, so we can assume that the dust event is the one that is generating the natural source for PM, and then this natural PM can affect health, as well as the local PM, which, as I mentioned, mainly comes from vehicle anthropogenic sources or vehicle exhaust. So, but once again here, the research question is completely different from the previous one. So here, the research question is, are the natural and local sources of PM independently associated with a health outcome? Here, the good thing is that it allows to estimate the exposure response functions that, if you remember from my first slide, then we need to use for health impact assessment studies. And under these health impact assessment studies, we can estimate which is the burden of mortality or the burden of morbidity that can be used to implement new policies on reducing air pollution guidelines. So the idea is that here we can split our time series for the PM data in two components. So the local source, that one, the local source and the local source below at the bottom panel and the natural source at the top panel. Of course, those days non-affected by dust, they will have a contribution of 0 microgram per cubic meter of PM due to the natural source. But recent studies have showed that the dust event not also brings the natural source to the PM, it can also affect the composition of the local source of PM. So here we can define a kind of three-source model that will helps to answer not only the previous question, but also will help to answer if there is any association between the local sources of PM with a health outcome in a different between dust and non-dust days. Because the mixture of PM of natural and local sources, even within the dust days, may be different. However, the thing that we already checked in previous studies that we did in Barcelona and Rome is that for the Western Mediterranean cities, this approach works quite nicely, seeing that the natural source of PM does not affect health. The one that affects health is the local contribution to PM, but even more, the local contribution to PM during dust days, because it seems that the height of the boundary layer is reduced during dust events, and it compresses the pollutants. It generates a new kind of chemical reactions, making the pollutants more toxic for human health. But we have seen that for the Western Mediterranean and the Middle East, it seems that this fancy approach does not do as well as we thought, because for most of the cities, at least in the Middle East, the daily levels of local pollution during non-dust days are quite high. So, oops. Let's go. And then as a summary for this workshop, so remember that from the previous lecture, we already summarized that the time series studies can provide evidence on the short-term effects, are the ones that providing evidence on the short-term association between environmental exposures and health outcomes. Time series regression is the way that we use to, the method that we use to analyze the data. And the regression models for time series are in similar, using the same principle of any other regression analysis, but with some specific features that they are mainly coming that we need to control to adjust for the time trends and also for the time varying confounders. Remember the case of the air pollution? So air pollution is affected by the time trend, but also for another time varying confounder, which is temperature. But temperature is affected by time trends, but not for other time varying confounders like air pollution. So therefore, or even more, you also need to be aware of the different shapes of the exposure response and the lag effects of the environmental risk factors based on the epidemiological literature. So once again, for temperature, the exposure response is non-linear, U-shape. And there are two different effects for heat and for cold. And for heat is at the short term, up to 1 week most, but for cold is showing longer, larger effects up to 3 weeks. While for most of the air pollutions, the shape of exposure response is mainly linear, and the lag effects are a very short term, 2-3 days maximum. And I think it's all the stuff that I had available for this lecture. So at the end of the previous lecture and at the end of here, you have some useful references that I strongly encourage reading on the use of the time series regression, the time series regression design, and also in this one you have useful reference for some specific features, not only of the modeling, but also to assess for the effects of temperature, air pollution, and desert dust. So thanks for your attention. Thanks again. Thanks again also to Marco and the organizers for the invitation and for your patience with all the technical issues that we have during this conference workshop.
Thank you very much to Aurelio for a wonderful presentation, a very illustrative presentation. And I think with this, what I would like to do is, since we still have a few minutes on the scheduled time, I will open the floor for questions from the participants. We already have one question that was submitted a few minutes ago by Maribel Casas, and she wants to know, Aurelio, whether with lagged effects, and you were talking about the lagged effects of temperature at the time, whether we can estimate a kind of long-term effects of the exposure I don't know, Maribel, if you are listening, maybe you can unmute yourself and ask the question directly.
Oh, yeah. So, hello, Maribel. So, because I know, Maribel from Barcelona. So, so these methods are not. I mean, when I'm talking about long-term effects, I refer to chronic effects, and with daily data, it's quite difficult to get an estimate of a chronic effect because chronic means years of exposure. Of course, you can use somehow this methodology, but not with, or this design, not with daily data, but mainly with monthly or with annual data. So in that case, any given lack of exposure will be with a meaning of 1 year and will be helpful to address for long-term effects. Otherwise, the only alternative is just to use individual data, but with cohort studies. So you need to follow all the patients for a set of patients for a very long time.
Okay, can you hear me, Aurelio?
Yeah.
Okay, thanks. Very nice presentation. Yeah, I was wondering because we are using these models, the distributed log lag nonlinear models, to assess, for example, exposure or cumulative exposure since pregnancy until childhood, and only take one outcome as variable. So we don't have repeated measurements of our outcomes. Sorry. And for example, I don't know, we have lung function or working memory or whatever. And at what extent can we use these models to assess this kind of health effects?
I mean, you can use, as far as I remember, there are several examples already published using distributed lag nonlinear models.
Yeah.
But yeah, they only need. I think that your problem is more related with the assumptions that you need to make because you are not having repeated measures over time than the models themselves.
Mm-hmm. Okay.
But if you like, I mean, you can send me an email and we could have a look to the data or the assumption that you are making to apply these models.
Mm-hmm.
But
okay,
yes, of
thanks.
course, yeah, it will be ideal if you already have repeated measures over time. Then the way to use it will be exactly the same, because this set of models can also be applied under different approaches, not only Poisson regression, maybe also survival analysis.
Yeah. Okay, thanks, Aurelio.
Aurelio, the next question comes from Andrea Castillo, and she says, "Thank you. About association with temperature, are you using daily mean temperatures or min-max temperatures?"
We are mainly using daily temperatures, but there are studies already published with daily maximum temperatures or even daily minimum temperatures. So we already published study in summer of the health effects of heat during nighttime using daily minimum temperatures, because the daily minimum temperature mainly occurs at nighttime. So you can do both, but once again, you need to set up which is your research question. So daily maximum temperatures, they are mainly used to address or related when you are trying to assess for extreme heat or even heat waves, and minimum temperatures when you are trying to assess for example, nighttime effects of temperature.
Okay, thank you.
Okay, now we have a question from Samuel Osorio that says, "How does the central limit theorem apply to time series analysis?"
Oh, it applies in the same way that in any other situation. So because the central limit theorem, it mainly applies on the parameters. So you can assume that the parameters, which in fact are average effects, are always distributed normally. One thing is how the data distributes, that in our case is Poisson, but the parameters are averages, are means, in fact, mean effects. They are always distributed because of the central limit theorem normally.
Okay, I hope that answers someone's question. Maria Christou says, thank you very much for an interesting and useful presentation. And she wonders whether there's going to be a practical component to the session, a practical element to the workshop.
Ideally, the workshop was originally planned to be run on site, face to face, in person in Cyprus. But unfortunately, due to the travel restrictions because of the COVID pandemic, the organizers, they decided to run it in this short format on 2 hours. So the thing that I did is that in the website with the course, with the workshop materials, you have available the slides, so the presentations that I ran, and also all the scripts, functions, and dataset that I did use to generate these examples. So now is the practical part of the workshop. I'm sorry, guys, it's really up to you. You can download the files and you can run it by yourselves in R. And of course, if you have any questions or any trouble, I mean, just let me know.
Okay, and here I want to make a comment to something, a question that I have received from a few people already, and it pertains to the availability of the recording of the workshop. After today, we are recording the workshop, and I need to clear the hosting situation, and also need to talk with Aurelio whether it's possible to make this recording available at least to the participants, not to the wider public. So if we end up doing it, if we host the recording, of course we will inform all of you via email. We have your emails from the registration, so you will receive an email with an update if we make this recording available for later download. The next question comes from Riol Caicedo, and says, how can we take into consideration the effects of behavioral changes, such as during national holidays, or for example, behavioral changes during Ramadan?
Oh yeah, I didn't mention this because it was too short. We can account for these behavioral changes by fitting indicator variables into the model. One of the variables that we used to fit, besides the time trend to adjust the long-term trends and the seasonal pattern, are also variables related with the weekdays and also with public holidays. That in your case you can fit an indicator variable taking the value of 1 for those days during the Ramadan and zero otherwise. So even in Spain and in most of the studies that we did conduct in the Southern Mediterranean, we already use a kind of variable for the summer holidays, because here between 15 July to 15 August, I mean, all the people there live in the city. So these kind of behavioral changes, as you mentioned, can be controlled by fitting dummy variables into the time series regression models.
Okay, fantastic. Thank you very much. The next question comes from Niria. I don't know what the name is, but I guess the last name is Niria. And it says, I would like to analyze the health effects of air pollution, but I only have weekly epidemiological data. Would I be able to see the effect?
Oh, that's a million, not million, but at least a couple of €1,000 question. So the problem is that using weekly data, you will collapse the effect into 1 week. And as I have shown and mentioned several times during my lecture, the health effects of air pollution are mainly short-term, 2 to 3 days. Of course, you can run the same analysis, but the analysis using weekly data will be a kind of average analysis where you will only be able to find for weak effects. And it is very likely that no, let me think, let me rephrase. If there are strong effects during the first days, so it could be likely that you will find the same effect or at least a reduced effect using weekly data. So if you remember my example on ozone, when looking at the exposure, at the overall exposure response function after collapsing the lag dimension, there was a positive slope of the risk of mortality, but it was not, let's say, statistically significant. But when checking lag by lag, we found, or I showed that there was a significant effect, positive and significant effect in the day 1, 2, and 3. So the thing, it's very likely that the thing that you will find is a positive effect, and it will become significant or not depending on how strong is this effect on health during the first days of exposure, because you cannot disentangle for the whole week. You will have all week already collapse. I mean, you can do it, but then the interpretation could be a bit tricky, especially if you are not getting statistically significant effects.
Okay, thank you very much, Aurelio. And I have not received any more questions. So if anyone else has a question for Aurelio, this is the moment. Please just unmute yourself and ask the question. Otherwise, if there are no more questions, okay, there's one more question from Oka at Nies. It says, how can I determine the best degrees of freedom, I guess, DF, for parameters considered?
Oh, this is another couple of €1,000 question. So if you are talking about the degrees of freedom for the time trend, so it's a bit tricky. So because as much as you increase, so if you are trying to use a kind of statistical criteria, like for example the log likelihood or the Akaike value, the thing that will happen is that since your only explanatory variable in your time series regression model is the time, so it will adapt. So every time that you increase the degrees of freedom, so it will fit better, because there are only these variables to trying to explain the whole time series data. So here, instead using a statistical criteria, you need to use a kind of trade-off between the epidemiological knowledge and the visual inspection of the fitted values, as I did in my presentation. So you need to think that each degree of freedom that you are using per year is a change of direction within the seasonal cycle in that year. So you can use most 12. That will be a change in direction for each month. So we used to run between 2 and 12 and then compare by once again visual inspection the fit of the fit of the data, and also how much the auto-residual the residual autocorrelation is reduced after increasing the degrees of freedom. So the idea is that try to don't over adjust. As far as I remember, in R, there are a couple of functions that they look automatically for the best degrees of freedom to adjust for any given variable. If you use this automatic procedure for time trend, it's quite dangerous because it will overestimate the degrees of freedom that you need. For temperature, it's much easier because these U shapes can be modeled with 2 to 4 most degrees of freedom. But the real trick is how much degrees of freedom you need to use for time trend, and it's mainly based on the experience on your own experience analyzing data, the literature review, and the visual inspection of the model fit that you are trying.
Okay, thank you very much, Aurelio. We have another question from Susana Silva that asks, can we convert weekly data to daily data? If yes, which method do you suggest?
No, weekly. You can convert daily data into weekly data, but you cannot convert weekly data into daily data. Because if you have the daily number, you have the weekly cases or influenza, or the weekly cases now of COVID, or the weekly mortality, you don't know how many of they were diagnosed or they die in each of the days of the week. So you cannot move down from a higher scale of time to a lower one, but you can move from a lower to a high.
Okay, Susana Silva again is asking, do you think it is possible to use the same value over all weekdays?
Oh yeah, I mean, you can use it, but then you will get exactly the same results if you analyze the weekly data.
Okay. Susana says thanks a lot. I see that actually Dr. George Christofidis, who is the coordinator of the health task force that which I'm a part of, and together with Camille Guller, who's also attending, he has joined this event, and I don't know if George wants to say anything about the meeting in general and the workshop that we just finished.
Yeah, no, really. I mean, thank you very much, Aurelio, and thank you very much, Marco, for organizing that. That was a great session. Thank you.
Okay, thank you, George, for attending.
Thank you.
Aurelio, sorry, did you want to say something?
Oh, no, I was just thanking the nice words from George. So thank you both.
Okay, we have one more question from Nicolas Valdez that says, okay, no, it's not a question, which is just a comment. Okay, so if we don't have any more questions, then I think we are going to thank again Aurelio for a wonderful session. And I will encourage everyone to keep tracking the events of the second conference on climate change in the Eastern Mediterranean and Middle East. And thanks again for joining us and for all your questions and your interest. We have over 80 participants, so I think this was a great success, I'm sure from all over the world. I hope it was useful to all your research independently, and nothing else to say. Thanks again, Aurelio, and I'll see you soon.
Thank you. Thank you everyone for attending, and sorry for the technical issues at the beginning.
I think technical issues have become a normal part of life since we are all working under remote conditions, so no problem at all.
Okay, thank you.
All right, bye.